Hey everybody, Trey here. Welcome back to another video. I'm sure many of you recognize my very special guest today, Storm Prediction Center meteorologist and forecaster Chris Broyles, back for another video on the channel. Today we're going to talk about a case that's been all over the news as of late, and that is the severe weather outbreak that occurred on June 20th, 2025 across most notably North Dakota, which included the Enderlin, North Dakota EF5, the first official EF5 in the US in 12 years. In this video, we're going to talk about some of the tools that Chris and other forecasters use in the lead up to this case to make their forecasts. And also we'll look at some radar data that shows some pretty unique things in the lead up to tornadogenesis with the Enderlin supercell. So Chris, once again, thanks for joining me. How are you today?
I'm doing good. Trey, I really appreciate you having me on. I think the Convective Chronicles channel is top-notch. It's a great forecasting resource. The Enderlin tornado event was very unusual, being in late June. The radar was also interesting, and we're going to go over some of those things coming up here in this presentation.
Absolutely. So with that, let's go ahead and get started.
All right, we're going to talk a little bit about the SPC forecast that was made for the Enderlin, North Dakota case for June 20th, 2025. I was at the SPC for this event and did the forecast with my other colleagues, and we looked at several tools for this forecast, and I'm going to go over some of those tools and explain how we use them and how they did for this event. The first one is the Omega Tornado Probability Tool, which stands for Outlook Machine Ensembling Algorithm. The 24-hour forecast had a 10% tornado probability in southern to southeastern North Dakota, with a 5% extending eastward to Wisconsin. The mega tornado probability is used to help us discriminate moderate and high risks, but it also forecasts all tornadoes. And on this day, it was suggesting that the highest tornado risk was in southeastern North Dakota. The mega tornado probability uses the significant tornado event probability, which we know as STEP, and this one here is for EF2 and greater tornadoes. And it was showing a 10% in southeastern North Dakota. And it was a very good forecast from STEP. The other tool that goes into Omega is the Locan tornado probability. Now, this one was developed for all tornadoes, and it shows a 10% from south central to southeastern North Dakota all the way over to far northwest Wisconsin. And the two together give us Omega. And this tornado tool is very good. We've used it for several high risks and moderate risks over the last several years. The next thing I'm going to show you is the 500 millibar ICE-ATACS and the 700 to 400 millibar DPVA. It's differential positive vorticity advection. And that is used to estimate what the lift is going to be across a given area.
And this is from the NAM model, the evening before the event, valid for 3Z, which is going to be 10 p.m. on the night of the event, correct?
Yes. So this would be, this was used for the 60 day one outlook. This is the NAM 27-hour forecast. Now we can see the 500 millibar jet was well to the west, and the blue contours show the 500 jet. The max there over northern Nevada of 75 knots. And that was coming in from the southwest, but it was pretty far back to the west. But also notice that there's a small little feature coming through northern South Dakota of about 50 knots. And if you also notice in the purple contouring, the dashed purple contouring, the DPVA, there were 3 bullseyes, one in North Dakota, one in South Dakota, and one that was very close to the Fargo vicinity. And so that was suggesting that there's going to be plenty of lift necessary for tornadoes. And then looking at the 24-hour forecast for the significant tornado parameter, it shows a 10 to about 11 in far southeastern North Dakota, just south of where the Enderlin tornado happened. And if we go to the 3Z, which is just a 27-hour forecast 3 hours later, it has an STP's bullseye of greater than 12. And so that is a very significant high-end STP. But the problem with that is that, and this made the forecast difficult, was the 700 millibar temperature was so warm for this case. We had 18C at 700 millibars just near the South Dakota, North Dakota state line. And your 700 temperatures were as warm as 15, 16C in the Enderlin area. And normally, we don't normally see high-end tornadoes above 12C. So it kind of gives you an idea of how unusual this case was. And it did throw some uncertainty into the forecast as well. And you can see it here at 3Z. I mean, that SCP is helpful. But again, it's in a very warm aloft environment. So what happens when we run the high-risk discriminator? This tool was developed to differentiate moderate and high risk at the SPC. And we've used this tool over the last couple years. This is a 24-hour forecast, valid 0Z on the day of the Enderlin tornado, and it was this forecast was available for the 6C day 1 outlook. And so when we want to see a high risk signal, the two highest numbers for the 0Z and the 3Z should add up to greater than 20. And on this day, you can see that the value is only 5.8 when you add the 0Z maximum and the 3Z maximum. So well below the high risk threshold. Next, I'm going to show you the 3-hour significant tornado event probability. And these are 3-hour forecasts. And you can see that it had a 40 there at 0Z. And so that was the maximum number there in southeastern North Dakota. And so that was why the 24-hour step had a bullseye, a 10 in southeastern North Dakota. It's not a particularly high number, 40, but it is something that will catch your attention.
And just for some context, in the April 2nd case, the Lake City, Arkansas event, we were seeing step values approaching 70 or getting to 70, which is extremely high, correct?
Yes. A 70 is officially a high-risk forecast from the 3-hour step. So it gives you an idea of what we're looking at here. And the warm air aloft was probably a strong player for why the step was not higher than a 40.
Chris is now going to perform his analysis on the 500 millibar jet translation speed as espoused in his paper on the Omega project. To do this, we first find the centroid of the jet maximum at 500 millibars at 6Z the night before the event and at 0Z the evening of the event. We then calculate the straight line distance between the two centroids and then divide that number by 18 hours to get our translation speed of the 500 millibar jet.
When we look at the 500 millibar heights and isotax, this is for 6Z June 20th. So this would be the night before the Enderlin tornado. And you can see there was a mid-level jet there in far southwest Utah. And you can see the jet streak there. I've got it, the centroid mark with a little red dot you can see on that map. 9 hours later at 15Z, the jet has moved up into southern Wyoming. And that same jet streak then by 0Z on the day of the event was in central South Dakota. And the jet streak, again, we saw that on the NAM 500 millibar isotac forecast. And this is at 0Z. So it's just a little bit southwest of where that 3Z depiction was, but still you're in that exit region of the jet. And for, a jet to move from far southwest Utah to South Dakota in just 18 hours in late June is very unusual. Normally in the summertime, these jets slow down. We hardly ever see these jets moving this fast. So it did tip us off that there was something unusual about this event by just looking at the 500 millibar heights and isotax. So when we apply the 18-hour difference in distance, we got to 810 statute miles, which then converts over to 704 nautical miles. You take the beginning point at 6Z and the end point at 0Z in that 18-hour period, and then you get the distance, and you divide by the 18 hours, which gives us a translation speed of 39.1 knots. And generally what we want to see is greater than 40 knots for a tornado outbreak, or in this case, maybe more of a smaller cluster, but a higher end tornado event. This is just a tornado event. I wouldn't really say it was an outbreak because it was such a small confined area. But anyway, 39 knots in late June is very unusual. It's a very fast moving jet. It's very close to that 40 knot threshold that we use. So it did kind of tip us off that this could be a bigger day, tornado relative wise. When we look at the significant tornado parameter, we take the highest 1 hour value between 18Z and 6Z. And so when you flip through all the STPs between those, the 1Z was the highest STP within that 12-hour period, and it had an STP max of 10. And this is from the HREF. This is, again, this is a 25-hour forecast from the HREF from the evening before, valid for the 6Z day one outlook. And so when we use those thresholds that we looked at on the previous maps and enter them into the tornado outbreak indicator webpage, the TOI webpage, the probability of verifying high risk was 41%, which is actually a pretty respectable number in late June. And because we were not dealing with, we didn't even have the outlook at moderate risk for the 60 day one. It was actually just a 5% tornado probability. So we weren't even really thinking about the possibility of high risk because, we were just at enhanced actually before. So we weren't really thinking about high. So, but in retrospect, we went back and did enter the numbers into the webpage. And so you can see that, it was expected to be, the TOI webpage was forecasting a relatively big day. And so this was the outlook that I was working 60 day one outlook, and this is the 1730Z update day two outlook that Ryan Jewell did. And he had an enhanced over North Dakota, extending into Minnesota. And he had a 5% tornado probability. This was the updated day two outlook at 1730Z. So the day before the event, we were thinking gradually just basically a 5% from North Dakota into Minnesota. But the main thing for that outlook was he had 30% significant wind probability across that same general area. And we were thinking about a damaging wind event or a wind swath. And that would potentially extend all the way into the Great Lakes with the main threat area across North Dakota. And then a little bit smaller of a SIG hail area as well. And so using the Omega tornado probability, it seemed prudent to add a 10% in. The Omega tornado probability does verify very well, but we also had the lift that we needed, and we had a high STP, and then the warm air aloft threw a lot of uncertainty in. So the thinking is that the warm air aloft would keep the convective coverage less so that the tornado event might be a little bit more confined. So the 10% probability upgrade seemed to be the way to go. And so for the 60 day one, a 10% SIG was added in for southeastern North Dakota and western Minnesota. And then the 30% wind and 30% hail was just kept. Then on the 1Z day one outlook, the upgrade was to moderate, and that was for potential derecho that was coming in across western North Dakota and was expected to leave a wind swath from central southeast North Dakota into Minnesota. The 10% SIGTOR was held for that outlook at 1Z, and then the wind outlook was upgraded to a 45% SIG, and then derecho was added to the text. And we did get a derecho for this case. It did work out. There was a swath of high winds with SIG wind gusts from central North Dakota all the way into northwestern Minnesota. And the SIG hail was just kept, the 1Z outlook. And in the end, the Enderlin tornado event was ended up having an RIV of just over 5. And with the risk impact value, we expect high risk events to have 4 and greater. But in this case, with the RIV being greater than 4, we still probably wouldn't expect to go high risk on an event like this because the tornadoes were clustered in such a small area. We did have the EF5, but it was a short track, and we had only short tracks on this day. If we had had several long track tornadoes and then the Enderlin EF5, then we would be thinking that high risk might be the best call. But on this one, with only 21 tornadoes, relatively short tracks, I think a 10 sigtor or a 15 sigtor would be the preferred outlook forecast. Now we're going to take a look at the Enderlin supercell and the EF5 tornado and look at some radar. This is hypothesized based on a database of about 250 events. We've looked at reflectivity and base velocity to show where the boundaries were and the features that contributed to tornadogenesis for the Enderlin tornado. In this depiction here, this is the reflectivity at 324Z on the evening of June 20th. This is looking from Grand Forks, North Dakota. The forward flank downdraft boundary, you can see that drawn west, northwest, east, southeast along the forward flank of the supercell. The supercell is already developed at this point. It has a RFD, or a boundary that extends from an inflow notch down south and southwestward. This is about 38 minutes before the tornado. And you can see the flanking line there to the northwest of the meso. And so what we're going to do is we're going to run this out in time. I'm going to show you how these boundaries moved and how tornadogenesis was played out for the Enderlin supercell. So this is at 0330Z, or about 0331Z. This is about a half an hour before the tornado. And you can see that the mesocyclone is just above the RFD boundary. We see that 2 cells develop within the flanking line, one to the west of the meso, one to the northwest, a little bit further away from the meso. And those 2 cells move toward each other until they merge. There's a cell merger there at about roughly 19-20 minutes before the tornado. And this is a key merger. So you can see these 2 cells will go back, just move toward each other. And this is often what we see with these kind of storms that produce high-end tornadoes, like the Cole, Oklahoma EF3 tornado. There was a cell merger very similar to this. And then the Salersville, Kentucky tornado. That was an EF3 in Kentucky on March 2nd, 2012. Also had a very similar setup where 2 cells within the flanking line converged. Now, we don't always see it happen like this. Sometimes the cells will actually be much further west, and they will be away from the supercell itself, so they're not going to be in the supercell, and they come and then merge into the flanking line. But in this case, the 2 cells formed in the flanking line. So this is more of a rare case. We don't normally see these kind of mergers in the flanking line. They typically are separated, but they can happen this way. And about 10 to 15% of the storms that produce, violent tornadoes look like this. So we'd had this merger here to the west of the meso, and then from that, a descending reflectivity core developed just to the west, southwest of the meso. And I want to point out that as the cells merged, right here, you see the RFD boundary surge out to the northeast, which pushed the boundary away from the meso, actually undercut the meso. So now the meso is sitting over the RFD, and as the RFD surge continues, the meso moves back further into the rear flank downdraft, and an inflow channel develops. So we'll see to the north of the meso, there's a corridor that's pretty narrow where the inflow is forced to go through. And so what happens is the window in which inflow is entering into the mesocyclone decreases, but the mesocyclone doesn't change the strength. It just keeps continuing to pull air up from the ground, from near the ground and upward through the meso. So what happens is you get a pressure deficit that develops beneath the meso. So as you evacuate a lot of air aloft, you can't quickly replace the air underneath it, so the pressure must drop. And so then you get a surface low that develops in the river flank downdraft. And so that's what we saw this day, was there's a surface low in the RFD beneath the meso. The inflow channel was organizing at this point, but the RFD surge continued, and now we're only about 6 minutes away from the tornado. And see that the DRC, the nose of the DRC, is now in the vicinity of the RFD occlusion, and the DRC still moving to the south of the RFD occlusion, but you can see that the DRC is kind of wrapping around the circulation, and the inflow channel now is going to start to move around the RFD occlusion as we approach tornado genesis. This is about 3 minutes before the tornado, and at this point, the DRC core actually starts to break off from the nose of the DRC, which is kind of unusual. We don't normally see a split like this with the DRC splitting into two. But you can see the inflow channel there working its way back around on the west side of the RFD occlusion. And now you can see that the inflow channel is pretty long and narrow, and actually a lot of air is being forced through that small corridor. And so the RFD occlusion is going to continue to drop because the mesocyclone is trying to get more air below to replace it. So it's just lifting up a lot of air through that broad circulation of the meso. And then as the inflow channel connection is made, that's about the time the tornado formed on this case. You can see that the tornado formed near the DRC nose. And like we've seen in so many other cases, the DRC is an important part of tornadogenesis. This is about 2.5 to 3 minutes after the tornado start time. And you can see that the Enderlin supercell was very well organized, had a very well developed inflow channel, and about the time when the RFD surge is done. It's about done here, but it continues to organize. You can see that inflow channel still there, and it's even getting narrower, which is just sign that the storm is really strong at this point. And so let's take a look at the cross-section. So can we see evidence of the DRC in the cross-section? I think this case is interesting. You know, it was pretty far from the radar, and so it was a little bit more difficult to analyze. But this is a cross-section we've drawn from where the cell merger occurred and along the track of the DRC. When we look at the cross-section, the surface is down at the bottom of the image, and then it's 60,000 feet at the very top, and then those lines are separated by 10,000 feet. So we're looking up we've sliced through the storm, and we can see initially that it looks like there's several depictions of what could be multiple cells there. And this is about almost half an hour before the tornado. So you have that cell merger that we saw in the reflectivity planar view. And it kind of appears like that could be happening in the cross-section. And at this point, then we see on the next frame, this is showing that maybe the DRC is forming. And then we see this little piece that just kind of drops downward through time toward the surface until it reaches the surface at about the same time the tornado forms. And so this is the same thing that we see over and over and over for these high-end tornadoes. You have a cell merger followed by a descending reflectivity core, which then gradually drops down to the surface. And when it reaches the surface, that's when the tornado forms. And so the Enderlin case was like so many other cases that we've seen that have produced violent tornadoes. But the question is, could we see this in the velocity data? And initially, we do see somewhat of some winds associated with the DRC appears, but then there's a data gap here. There's no data. And when I was doing the analysis, I looked at the Aberdeen radar. Sure enough, the data void shows up in the Aberdeen radar. So, and Aberdeen was further away. So the Grand Forks radar showed us the best thing that we had. But we do see the DRC winds, it looks like, as we go toward the time of the tornado. So if you look back, you can kind of see that first image and then these other two images do show that it does seem like there's something coming down. And I can highlight that by drawing in the axis. So there's the wind axis there about half an hour before the tornado. And then the wind axis is going through the data void. And then we still see that wind axis until it reaches the ground and then at tornado time. So we do see some evidence of the wind speed of the DRC. But when we look at the reflectivity core, we definitely see that a little bit better. Again, this was further from the radar, so it was a difficult case to analyze, but it does seem to show the same characteristics that other violent tornado storms, including the Cole, Oklahoma tornado that was very similar in so many ways.
So that's going to wrap things up for this video. That was an excellent discussion of this case, Chris, and again, I thank you very much for joining me today to discuss this case. As we saw, this was a very unique forecast, very tricky forecast, and the overall evolution of the storm was quite unique. Do you have any closing words about this case that you'd like to say?
Yeah, I think it was a difficult forecast. It was a late June event with a violent tornado, which we don't often get a lot of violent tornadoes in late June. There was warm air aloft, and that presented uncertainty. And for the radar, it looked like a typical violent tornadic supercell, but the DRC split, which was very unusual. So it was a difficult case. We got the moderate risk, and I think that was a key. We got the 10% SIGTOR added in the evening before, and then the moderate risk was upgraded on the onesie, and I think that was really good. And I think it went pretty well. So.
Well, it was a very good forecast, so well done. Thank you again for joining me today to discuss this case. So that's going to do it for this video, guys. Thanks for watching, and we'll see you in the next one.